Hello, welcome back. Okay, so today we will talk about the last type of sorting algorithms covered in this topic, linear time sorting. Okay, we will discuss three types of linear time sorting algorithms: counting sort, RADIX-SORT, and bucket sort. Okay. And the name of, first of all, the name of this sorting algorithm family is straightforward. It costs linear running time to sort an input sequence. So this is maybe a bit counterintuitive because previously we have introduced quick sorts and heap sorts, and we also know that merge sorts. These three types of sorting algorithms, we already know that they have very efficient running time, which is n times logarithm of n, okay, which is a higher order function compared to a linear function. So how could we do better? Then, of course, this linear time efficiency comes with a constraint or a condition. It's not that any type of input can achieve such a linear running time efficiency. So let's start from the counting sort. Okay. So the constraint for this type of sorting algorithm is that it assumes that each of the input elements should be an integer, and that integer is within a range, within certain range between, say, 0 and k. Okay. And utilizing these constraints or condition, then we can basically achieve a linear running time efficiency. So when the range of the integer elements is also bounded by the length of the input, it runs in big theta of n time. Okay. So the idea behind is that for each input element, it will count how many elements within the sequence are less than x. And then it will use this information to place the elements into a correct position in the output. Right. So any type of sorting algorithms, eventually they want to achieve a sorted sequence. Right. Each element is in the correct position. And to the left of the elements, these are all the smaller elements, and to the right of it are all the elements that are larger than it. So this type of thinking makes sense because we eventually want to decide the proper position for any elements. Okay. So,
I'm sorry. Like, is this the midterm review or is this the new lecture?
This is the new lecture. This content will not be in the midterm.
Okay. Are we gonna do the midterm review today, or is that?
No, we are already done it. We have already done it in the Thursday's lecture.
Okay.
Okay. So we'll basically need to count how many elements, the number of elements that are less than the current elements. Okay. Say, for example, if there are 17 elements that are less than x, then this x must be at the position 18 because there are 17 elements that are less than it. Okay. So let's look at the procedure directly. Say our inputs is an array that has n elements, and we need other two arrays to help implement this algorithm. Okay, we first need a B array, and B is also the same length because it is used to hold the sorted outputs. And the C is a special array. It has k+1 elements. Okay, so it's from 0 to k for temporary working storage. Okay, and we will basically see why this will work. Okay, so this is the counting sorts, the pseudocode implementation for the counting sort. So we're not going to analyze it here, but we can first quickly analyze the basic sketch or basic structure of it. It takes inputs, the input sequence and the outputs and the k, which is the range for each integer element. So we can observe very obviously that there are four loops, right? Okay, the range of the first for loop is from 0 to k, right? And the second for loop iterates over all elements in A. And the third for loop iterates over 1 to k again. And for the last for loop, it iterates over all the elements in A again, but in the reversed order. So that's basically 4 for loops. Okay, so that's why, and there, more importantly, there's no inner for loops or inner while loops. There's no nested loop structure. So, and it's easy to infer that the running time is bounded by a linear function. Okay. Okay, so let's look at the functions for each line in this pseudocode. Okay, and first of all, we'll initialize the array C to all zeros. C contains k+1 elements from the index 0. So this is a kind of a special case because conventionally we have established the rule that we start from index 1 in the pseudocode of this course. But here we're making an exception because we're really not using that zero index elements because it's basically for the purpose of more the next step computation here. We need to access I-1 of C. So if we initialize C0 to be 0, then it will be convenient for the next. So we can avoid the out of boundary errors in the code. Okay. And that's the function of the first for loop. We initialize all the elements to 0. And the next for loop that iterates over the input array A is critical because it basically inspects each input element in A. Okay. And if the value of an input is I, then we need to increment the elements in Ci. Okay, the elements here. So the value of that input of that element in A, if it's I, then we will need to increment Ci. So this I is not the index in A, but the value of the element in A. So that's why we are using the value Aj as the index in C. Okay, because we make sure that all the elements in A is within the range between 0 and k. So this using the value as the index in C will never cause the out of boundary problem in C. Okay, because that's the condition we have. That's the constraint we set on the input array. So by incrementing the elements in C at position Aj here, we are actually counting the number of appearances of certain value in the input array A. Okay, so after line 5, after the second for loop is executed, the element at Ci should hold the number of input elements that have I as its value. Okay. So C0, for example, C0 should hold the number of elements in A that has the value 0. And C1 should hold the number of elements in A that have the value 1, and so on. All right, that's the second for loop. And the third for loop works on C, and it reiterates over 1 to K, right? And it's basically sum the current C with its previous, with the elements to its left. Okay, it's plus Ci to I minus 1. So we call it a running sum because we work from left to right, and basically this operation determines how many input elements are less than or equal to I by keeping this running sum. Okay, then the first 3 for loops are to make the necessary preparations needed for the last for loop. And this last for loop iterates over A, and the job of it is to take the elements from A and use the helper array C to determine the correct position that we need to put that elements in the output array B. Okay, so right here, this the order of the last for loop is a reverse order. We start from the last elements, and we'll explain that why we have such a reverse order for loop. And taking that elements out from A, we can have its value by Aj, right? And we take the value of Caj again. And the Caj actually, according to the third for loop, it contains the number of elements that are less than or equal to Aj. Okay, so we use that information to put Aj into its correct position in B. Okay, and the C of Aj is the correct final position of the elements Aj, because there are that many C of Aj, many elements that are less than or equal to Aj. Okay, so if we can recall the previous example in the previous slide, it's a more concrete number. We say that if there are 17 elements that are less than or equal to the current elements, then these current elements must be placed at the 18th position. It's kind of this principle that we are applying here. Okay, and because the elements in A, they are not distinct. There could be multiple elements that have the same value. So each time after we take one element out from A and place it to B, we need to decrement the value of C of Aj, because such a value we have taken it out one of such elements. So that is the explanation for the code for counting sorts. And I think it will be easier if we go through it using a simple example. Okay. So let's use this input array that has 8 elements, and the values of the elements are described in a box. And also, here is what does array C look like after we have initialized all the values to 0. So after line 3, after the first for loop is executed. Okay, and then let's look at what the C would be, what the C array would be after the second for loop is executed after line 5. Okay, it will be like this. So the first element, C0. C0 stores how many elements in A are less than or equal to the value 0. So if we look at A again, we can see that there are 2 zeros. So there are 2 of such elements in A that are less than or equal to 0, to the value 0. So the C0 after line 5 is 2. Okay. And so after line 5, this is no, I need to make correction. So after line 5, the values in C is not the number of elements that are less than or equal to. It is just the number that it is a number of occurrences of such a value in A. So in A, there are 2 zeros. So after line 5 is executed, the C0 is 2, right? Because there are 2 elements, there are 2 zeros in A. And there's no 1 in A, right? So the C1 is 0. Okay, there's no elements in A that are 1. And C2 is 2 because there are 2 2s in A. Okay, and C3 is 3 because there are 3 3s here. Okay, so and so on. So here's the C, what C looks like after the second for loop is executed. This is not the final values of C yet, because we have the third for loop to execute. Okay, so the third for loop for the on the C will compute the running sum from the left to right. Okay, so after the third for loop is done, C0 is not changed, but C1 becomes 2 because this 2 is the result of 2 plus 2 plus 0. Okay, and the 4 here is 2 plus 0 plus 2. Okay, so that's the meaning of the left sum. So this 7 is everything to the left of this 7. Okay, so now after line 7, the meaning of the C's is the number of elements that are less than or equal to the values in CI. Okay, so C0 equals 2 means that there are 2 elements in A that are less than or equal to 0. And for this C1, it means there are 2 elements that are less than or equal to 1. And for 2, there are 4 elements that are less than or equal to 2. Okay, and so on. So now we are at the points before we execute the last for loop. Okay, so explain line 5 again. Yes. So let's just doing this more slowly. Okay, you are looking at the second for loop before line 5 again. So the loop counter is J. J iterates from 1 to 8, right? J will start from here, from 1 to 8. So first of all, we have A1. A1 is 2, right? So the AJ will give 2. That means we need to increment C2 by C2 plus 1. Because C2 was originally 0, right? So the line 5 will compute the new C2 by increment C2 plus 1, okay? And the second iteration of the for loop is J equals 2, right? Right, J equals 2 now, and the value of A2 is 5. So we will need to increment C5 by 1. Okay. And then J is 3 here. And A3 is also 3. So we need to increment C3 by 1. Okay. And then it's J equals 4, and A4 is 0. So we will need to increment C0. And then J equals 5, we have A2. A of I equals 2, so we need to increment C2 again. And 6, right? We have 3, and 3 have 1 more plus. And then 7, we need to increment C0. And lastly, we have A8 is 3, so we need to increment C3 again. So look at how many plus 1s we have will result in this first C array. Okay, we have 2, 0, 2, 3, 0, 1. So that's why we've got this C. And then further we will get the final C that we had that we need to have before the last for loops. Okay, so that is the first part before the final for loop. So let's look at what this last for loop does. Okay, and this for loop works on the array input array A, but in the reversed order. It starts from the last elements, and it will need to use the C to find the correct position in B for that element and place that element into B, and then decrement the values of the current C array elements by 1. So let's use this example again. So J will start from A, and we know that AJ is 3, okay? So we need to refer to the element C3, right? Because it's a C of A of J, right? C of AJ. So we need to refer to the element C3, and the value of C3 is 7, okay? And the meaning of that 7 is that there are 7 elements in A that are less than or equal to the value 3, okay? So we need to put the element 3 into the 7th position in B, right? Because C3 stores the number of elements that are less than or equal to the element 3. So in order to put it into a sorted order, we need to put that 3 into the 7th position in B. Okay, right? That's the results after we copied the element 3 to B into the 7th position of B. And afterwards, we need to decrement C of AJ, which is C3. Okay, because we take 1, 3 out from the input array A, and that means there are 1 less for the elements the total number the total number of elements that are less than or equal to 3 must decrease by 1 because we take 1 out, right? So the new 3 the new elements of C3 decreases from 7 to 6. Okay, so that's how the C looks like after this first iteration. Okay. If there are no problem on this slide, I'm gonna proceed on to the next. So okay, so let me put the current C here. And now the next iteration, we have J equals 7. And we have a counter 0. So A7 is 0. So we need to refer to the elements in C0, which tells us that there are 2 elements that are less than or equal to 0. So we need to copy that 0 to the second position of B. Okay. And then don't forget, we need to decrement C0 by minusing 1 from 2. And we got this, again, updated C array. Okay, let's move on to the next one. So next one, J is 6. Okay, AJ is 3. So we need to refer to the elements C3 again, but now we have a new value. It's no longer 7, it's 6. So there are 6 elements that are less than or equal to 3 now. So we need to put the 3 into the 6th position. So this is a good reminder that's why a good explanation why we need to decrement the C of AJ each time after we take the AJ out. Because if we didn't do that, now if we didn't do it last time, the C3 will still be 7, and we will copy the element 3 into B7, which is a duplicate, which is overlap, which is not correct. So we need to correctly decrement the C of AJ each time we take 1 element out. Okay, so now it further decreases from 6 to 5. C of D further decreases from 6 to 5. All right, so if we continuously do this until we reach the first element in A, then we will have the output array looks like this, and it is in the correctly sorted order. So that is basically how the counting sort procedure works. So now I would like to explain a little bit why it is important to keep in a reversed order. Okay, and you will actually find that the algorithm sort of works if we it'll give the correct outputs if we use the normal order. If we use the let the loop iterates from 1 to a dot length in the last for loop, but that didn't give a stable results. Okay, so we need to use the reversed order in order to make sure the sorting is stable, and that means the relative positions among elements that have the same values are preserved. The relative positions are preserved. Okay, so only by the reversed order, the first, for example, we have 3 3s in the input array 8, right? 1 3, second 3, and the third 3. Okay, so only by using the reverse order for loop, we can make sure that the last 3 is placed at the last position in B, and the second 3 is placed at the second position in B, and the first 3 in A is also the first 3 in B. Okay, so we can only preserve this by the reversed order for loop, because if not, if we use the normal order for loop, if we go through left to right order, then what will happen is that when we first encounter the 3 here, right? When we encounter a 3, then we need to refer to C3, right? Remember the original value of C3 is 7. So these 3 will be placed at this position, right? And the second 3 will be placed at the second position. And the last 3 will be placed at the first position. So that's scrambled order of the elements of the same value may seem not a problem, because if it's just pure integers, then all 3s are equal, then it doesn't matter, right? But what if these elements, they are more complex objects, and we are sorting them with some certain keys, and we want to keep the relevance positions of those objects, then these normal order for loop will not give a stable results. Okay, so the reversed order is a very important step, and it's a smart thinking here. Okay, are there any problems so far? Okay, if not, then let's go ahead and look at the running time for the counting sort. And actually, it is quite straightforward, right? We know that if a for loop does determining k requires a separate procedure. Yes, that's a good question. So so we'll basically need to enumerate or go through all the elements once to check what is the k, exactly k that we need, right? So I think that is the constraint we need to have on the input sequence. And so in this particular implementation, we let k to be one of the input arguments. So we require the user of this algorithm to determine the k for us. Okay. All right. So the first for loop. Yeah, I think you are making a good point, and you will see that procedure would not significantly influence the running time. So, for example, let's first look at the running time for all the for loops. The first for loop takes big theta of k time, and the second for loop takes big theta of n times, right? And the third for loop reiterates over k, so it takes big theta of k, and the last for loop takes big theta of n time. So altogether, it takes big theta of n plus k. Okay, so now let's turn to the question that if we need to determine k, then we need to, of course, we want to know what is the largest element in the input area is, right? We basically need at least one scan of all the elements in the array. So that is some linear time, okay? So if we consider that cost of determining the k, we are basically adding some costs on top of the big theta of n plus k. Right. So it will it comes with some cost, but it is not a higher order cost. So altogether, we can still have a linear running time algorithm. And if the k is bounded by n, then we can write it as big theta of n. Okay. So that is the cost for big theta of n running time. The big cost of counting sort algorithm. Okay. Let's look at the RADIX-SORT. Okay. I'm sorry, I need to leave for 3 minutes, so I will pause the recording now and be right back. I'm sorry about that. There's something in front of in the front door. I need to handle that. See you in a bit. Just take a break. Resume recording. All right. Now let's look at the RADIX-SORT. Okay. It's a very special type of sorting algorithm, and it's a quite old algorithm. And I think it's the first used in libraries that when people want to sort piles of documents that have holes that go through all the papers in each pile of paper, and there are fixed numbers of holes, and basically people can use a mechanical device to sort the piles of papers. And I believe there's such a YouTube that explains how this technique is used. Maybe I can try to find it and post it on Canvas. Okay, so let's quickly look at the purpose of it. RADIX-SORT is to sort a bunch of numbers that have fixed width, that has fixed number of digits in it. Say all the numbers are D-digit numbers, like either 2 digits or 3 digits or 4 digits, but each number should with fixed number of digits in each. So the idea is that we first sort on the least significant digit and sort on the second least significant digit. We continue this until all numbers have been sorted on all digits. And that is the results we need to obtain. Okay? And the key idea is that the key requirement is that the digit sorts must be stable. Okay, so each time when we use the digit to sort the numbers, we need to use a stable algorithm. By stable, we mean the relative positions of same elements, of same value should be fixed. Okay, so that said, we can use counting sort as a candidate algorithm for this that are used in RADIX-SORT. Okay, so let's look at an example here. That's there are 7 numbers, 7 3-digit numbers, 329, 457, 657, and so on. So our goal is to sort these 7 numbers. So the first step is to sort based on the least significant digit, right? Which is the first digit to the right-hand side, right? So we have the sorting results like this. We put 0 as the smallest, and then comes 5 and 6, right? And 7 and 7, 7, 9, 9. So if we just look at the last digit, this is the results for the first round of sorting, right? And we will continue this step using the second least significant digit, which is this column in the middle, right? The original digits, the original numbers are 2, 5, 3, 5, 5, 2, 3, and the results is 2, 2, 3, 3, 5, 5, 5. Okay, and the stables within this process, we are using a stable sort. So that means we have a 5 here and a 5 here and a 5 here, right? So the first 5 will appear here. The second 5 appears here. The last 5 appears here. So the relative positions are not changed. And that is a critical step. And if we look at the previous process again, we have 2 7s, right? The first 7 appears here, and the second 7 appears here. So the relative position also doesn't change. Okay, so that is the technical key points that we need to have for this type of stable sorting algorithm. So lastly, we use the most significant digits, the third digit, which gives us a output for the radix sort, which is 3. Which is 3, 3, 4, 4, 6, 7, 8, the results. And this is exactly the results we want to obtain out of the algorithm. Okay, so let's look at another stable sort results. The first 3 is here, and the second 3 is here. Okay. So as you see, by keeping the relative positions of the sorts, this algorithm can correctly sort all the numbers into the correct positions. And the implementation of this RADIX-SORT algorithm is also straightforward, because we know how many digits are there in each number. So we simply need to go through the lowest order digits, say 1, and to the highest order digits, say D, and we simply use a for loop to go through all the digits, and then within each for loop we need to use a stable sort to sort an array on digit I. Okay, so there's some there are different ways of implementing this depending on which type of data structure you use. If you use array, then there are different tricks to handle number in arrays, or if you use a higher level programming language, if you use an object to indicate a fixed digit number, then there are object-oriented ways. So here we are not going to dive into the details, because that is a very specific implementation that are suitable for different programming languages. But the idea is the same. We need to use the stable sorts to sort array on that digit I. Okay. So we previously have just known a stable sort algorithm, which is counting sort. So if we use counting sort in this case, then the total running time is big theta of D times n plus k, right? Because each call to the counting sort takes big theta of n plus k time. Okay. So this is also a type of linear running time algorithm, because the D is a constant. The D cannot be infinitely big, right? The D cannot vary. So when the input sequence is given, we can always like use D as a constant factor. So that's why the running time for RADIX-SORT is determined by a linear function of the variable n. It's still a linear running time algorithm. Okay, so that's for RADIX-SORT. And Any questions on the RADIX-SORT? If not, good. If not, then we're going to look at the last type of sorting algorithm, which is bucket sort. So this is also, I would say it's a pretty commonly used algorithm, especially when you're dealing with normalized numbers. Like if you have a bunch of numbers between certain intervals, then it is easy to decide the relative positions for each element, right? Because you can set buckets for each element. So the example we use here, it assumes that each input element is drawn from a uniform distribution. By uniform distribution, we mean that it's randomly drawn from a uniform or from a distribution that each value across that range is uniformly distributed. There's uniform chance that we pick any number within that range. Okay, so the average running time is big O of n. So, and we assume that the inputs is generated by a random process. Okay, and it will distribute the elements uniformly and independently over the interval 0 and 1. Okay, so we made a constraint that all the elements in the input array are between 0 and 1. Okay, and if this is not the case, it's also easy to convert the sequence to the range of 0 and 1. We just need to pick the largest elements in the array, right? And divided by that largest elements, then we'll have all the sequence elements between 0 and 1, right? If they're negative numbers, then we will first minus that the smallest negative number, and to make all elements positive numbers, right? So that's a condition. So the procedure is like, we divide that interval into n equal-sized subintervals, and we call this subinterval a bucket. We have a bunch of buckets. Okay, say we have n equally sized buckets, and we distribute the n input numbers into the buckets. Okay, and we do not expect many numbers to fall into the same buckets, because we assume that the numbers are randomly generated. So if the numbers are not from a uniform distribution, then it could cluster into certain, the numbers could cluster to some certain buckets. Okay, but that is not in our assumption. We assume that it is quite random numbers. And then we will sort the numbers in each bucket and then go through the buckets in order, right? We first sort each bucket and then go through the buckets in order by listing the elements in each. Okay, that's a straightforward thought, right? Because when we divide the buckets, they are already ordered, right? We know that all the elements in the second buckets are larger than the elements in the first buckets. Then as long as the elements within each bucket are sorted, then we can simply consecutively list all the elements in each bucket, and we will have a sorted result. Okay, so let's look at the procedure of the bucket sort algorithm. Right, we'll need to use a array B to help us. Okay, so we assume the inputs is within 0 and 1. Each element is within 0 and 1. okay? And we need to use an auxiliary array B that ranges from the index 0 to n-1 of linked list. Okay, so each element in the array B is a linked list, and we call each linked list a bucket. Okay, so its index is from 0 to n-1 because this is a more convenient way, because the elements ranges from 0 but is less than 1. So we are cutting the end. We're not using the 1 to n, but we're using 0 to n-1. We're including 0. Okay. So basically there are 3 for loops. Okay. So the first for loop iterates through all the elements in B and make each B an empty list. Okay, and the second for loop iterates over n, iterates over all elements in A and inserts A into the corresponding list B by using this flooring computation. Right, it times the length A. It times the length n with the value of the elements AI, because AI is between 0 and 1. So this resulting n, the results of n times AI must be a number between 0 and must be a number between 0 and n-1. Okay, because we used a floor operation. So, and that basically place all the elements in A into the bucket, throw all the elements into the buckets. And the last for loop is to go through each bucket and sort the list BI with insert and sort. Okay, so this insert and sort is not a mandatory or required one. We can use basically any sort of algorithms, but here, because insert and sort has well, it's easy to implement, and it's an elementary type of algorithm. It doesn't have recursive calls, so I guess that's why the textbook uses example. But actually, you can use any type of sorting algorithms to sort each list. Okay, and finally, you just need to concatenate the list from B0 to B1 to Bn-1 together in order, in such an order, then you will have a guaranteed sorted final array. Okay, so let's use an example to showcase the algorithm. And say we are done with the line 1 to line 4. We have initialized the B into a new array, and we have made an empty list for each element in B. And then we are at the step of the first for loop. We are now inserting the inserting the elements in A into the list B. Okay, so for the first elements in A, the floor of 10 times the elements A1 is 7. So we need to insert that elements into B7. Okay, and because each element in B is a linked list, so the B7, the 0.78 will be the first element in that linked list. There's an arrow shows the pointer that points to the head of the linked list. Right, and now we look at the second element in A, which is 0.17. So we do the computation, which is 10 times 0.17, which gives us 1, rounded to floor, which gives us 1. So we need to insert A2 to B1. Okay, and the third element is 3, so we need to insert that third element into B3. Okay, so that's the procedure we need to follow until we have put all the elements into the from A to B. Okay, so as if the A is a very random array and all elements are drawn from a uniform distribution, then they are more likely to be evenly distributed in the buckets in A. Okay, and this time we have just 10 elements. So it looks like some arrays in B have more elements and some other buckets don't have elements at all. But it doesn't matter though. We can sort now after all the elements are copied from A to B into the proper position. We need to sort each buckets, right? So right now, those buckets are not sorted. So we just need to call some algorithm to sort them, okay? So after that, now we have observed the sorted results, right? The B1 is a sorted linked list, B2 is sorted, right? So this is quite already very, we are approaching the final points. Now we just need to concatenate all the linked lists together in order, right? So it's a bit tricky to analyze the running time for bucket sorts because we have a random process here. We randomly draw numbers from a process and put them into buckets. So, but it turns out that it's a very efficient algorithm because when insert sort is used, it behaves pretty well on an average case, but it doesn't it doesn't do well on a worst case, right? So if we want to guarantee the performance, we can use some faster algorithms like quick sort or merge sorts or heap sorts. But even if the insertion sort is used, the total running time of bucket sort is still bounded by linear time. Okay, because when we analyze the worst case for insertion sort, we know that it is bounded by a quadratic running time function. Okay, so if we describe the solution to the total bucket sorts, we use a linear time plus a bunch of the summation of a bunch of quadratic functions, and here each ni is a random variable, is the size of each bucket bi. Okay, so even in that worst case, we can obtain the expected value for this expression by obtaining the expected value for each ni to ni squared. And we will find that the expectation or expected value of ni squared is 2 minus 1 over n. So you don't need to know how this is proved, but mathematically we can prove that the expectation is for each ni squared is n2 over 2 minus 1 over n. And if we substitute it into the equation here, we've got a function that is bounded by a linear function, by a linear time function. So this is very good news for us. So as long as we make sure that the input sequence is generated from a random process and all the elements are drawn randomly from a uniform distribution, then we can show that the running time for sorting that algorithm with inputs with the bucket sorts will gives us linear bounded time. Okay. So that's it for the 3 types of linear time sorting algorithms, and we are done with this chapter, the topic of sorting algorithms. So combined with the insertion sorts, and merge sort algorithms. We have so much sorting algorithms have introduced. So hopefully this table can help you have a better idea of what kind of running time accuracy or what kind of running time functions these sorting algorithms have. And one more thing maybe I can talk about more is that um, the insertion sort, merge sort, heap sort, and quick sorts, the first 4 types of sorting algorithms, they are more general sorting algorithms that are based on the comparison between elements. Okay, so these comparison-based sorting algorithms has a upper bound of time efficiency, which is the n times logarithm of n. So in theory, we cannot do better than this running time efficiency. But for special cases in the last 3 rows, if we set constraints on the input values, then we can do better using different types of tricks. I think that's it for the lecture today. If you have questions regarding the midterm, you can ask me now, and I will make announcements today and before the exam. I will also send out reminders. So basically, it will appear as a assignment. You will need to download a PDF file and also submit a document. Yes. So for detailed range of the midterm, you can refer to the slides that are uploaded for the review. It's okay if you just use a sheet to write down your answers. I don't have questions about matrix multiplication or max subarray problem. So, Jose, do you have class on Thursday? CS503, okay. Do you have class before 2 o'clock then? Because the schedules for everybody is different. Let me see.